topics, you would be surprised of how broad of this field. Okay, that before we did not aware of the existing of this field. So now we finished chapter 1, just an overview of the field. The first part of chapter 1. Okay. The second part of chapter 1, okay, I almost forgot, is a probability review. All of us are already taken the probability and statistics course, right? Not currently. Not all of us who haven't taken this one. Or but you took one in the undergraduate level, right? Okay, because actually it's a prerequisite for this course. Okay, but actually we are not going to use everything that you learned in that course here. Okay, so let's see what we are going to have to know about probability. Random event. Okay, event E, and the complement of the event, that would be, we use the E, C. C stands for complementary of the event. Okay. We have to concern about the concept of mutually exclusive. Okay, and the term the independent. These are two different terms, two different concepts. Okay, we use probability. Therefore, probability of event to occur would be in the range of 0, 0, and 1. Okay, the event and the complementary of the event, the probability combined would be equal to 1. Okay, with this Venn diagram representation, we see this one represent probability PE. Anything outside this set would be complementary of event, right? A 1 minus PE. So can we say that PE and probability of E and the complementary, these two parts are mutually exclusive? What does it mean, mutually exclusive? Okay, we come back to that later. Okay. For two events, A and B. Okay, let's see these two diagrams. Two sets, set A and B. We don't see any part share between the two sets. The two sets are disjoint, so this is mutually exclusive. Okay, but if there is a part that is shared by the two sets, this is mean that set A and B are not mutually exclusive. Okay, so A union B is calculated as probability of A plus probability of B, and actually plus the intersection between A and B. Okay, if A and B are mutually exclusive, then the intersection probability would be equal to 0, right? A and B, for this diagram, this situation, PA intersect with B would be equal to empty set, or probability would be equal to 0. Okay, so this term would be eliminated, gone. So we have only two terms, PA plus PB, mutually exclusive. Okay. What about if the two sets are independent? Two events A and B are independent. Then the probability A intersect B would mean probability that A occur and B occur can be calculated as the product PA and PB. What? This should be minus sign, right? So I'm waiting for someone to tell me what is wrong. Okay. So now we see the difference between mutually exclusive situation and independent situation, right? Next, if events A and B are dependent, then a conditional probability that A occurs given that B occurs, right, would be equal to this term, A intersect B over probability of B. If we change this term, write it the other way, we will obtain this equation. Okay. What does it mean? A occur and B occur would be equal to the probability that A occur given that B occur times the probability of B. Okay. So now let's see what about if A and B are independent? Look at this term, which is rewrite again here. Conditional probability A occur given that B occurs. Okay. For the independent assumption, A and B would be equal to PA times PB, right? So the denominator and the denominator would be cancelled out, right? The top and the bottom. So we're left with just PA. Conditional prop of A occurs given that B occur would be just the probability that A occur alone. Has nothing to do with B. Independent assumption. Okay. And this equation is a general one. Now let's see a little bit further of if A union B. From this general equation with independent assumption, A intersect with B would be equal to PA and times PB, right? And then we can represent this term with a different one. Conditional probability. PA independent assumption